from Colorado State and introducing a subject that I think we need to spend a lot more time on, dealing with error estimation. So.
Well, yes, thank you very much to the organisers for their invitation. It's a particular pleasure as a member of the Auckland diaspora to be able to attend this session. So what I've been thinking about recently over the last few years is error estimation and adaptivity for multi-scale, multi-physics problems. And of course, my hope is that some of these ideas will find utility amongst this community, and I hope that might be possible. So what am I talking about? I'm talking about systems that couple different physical processes which interact over a wide range of scales. And amongst the people at Colorado State that I work with, we've been looking at biological systems, ecological systems, fission and fusion reactors, meteorology, and some nano-manufacturing. So I don't need to tell you that there's a wide range of applications outside the interest of this particular group. We've studied coupling of various forms. You can have multiple physical components within a single domain. You can have multiple behaviors within a single domain that occur over different scales with different stability properties. So here I'm thinking of reaction diffusion systems. And Andrew talked about operator splitting. I assume that he was talking about solving a reaction diffusion system there. Or you could have coupling through a common boundary. These give rise to significant computational challenges, amongst them accuracy, stability, efficiency, and again you could be combining very different modeling paradigms. And again, Andrew talked about a Markov process, and that's a very interesting type of coupling that I haven't really made a lot of headway with yet, because the equilibrium configuration of a Markov process is some sort of probability distribution. So how do you exchange information between what is essentially a probability distribution and an ordinary or partial differential equation? So many of these systems, multi-scale, multi-physics systems, are solved through an operator decomposition approach, by which I mean I solve physics 1, I communicate either boundary conditions or parameters with physics 2, I solve physics 2, and based on that I pass information to physics 1 and I iterate forward in this fashion, either to find an equilibrium or to time march. The techniques that I will use or talk about are all based on the use of adjoints, and we call this adjoint-based a posteriori error analysis. And so the point is that the basic three-step process is to solve a forward problem in order to compute a particular quantity of interest. So all this work considers that you have a quantity of interest that you are interested in computing, some feature of the solution rather than the solution as a whole. I then solve an adjoint problem that is associated with the forward problem and that particular quantity of interest. And then the error in the quantity of interest is a convolution of the residual of the forward problem and a weight that's determined by the adjoint solution. And I also want to point out at this time that the adjoint to a system of differential equations or some nonlinear map also provides an efficient means for performing both forward and inverse stability analyses, which I've heard quite a bit of talk about over the last few days, but unfortunately that's a topic for another talk that I won't be able to dwell on. So in my operator decomposition approach, you saw a solution of physics 1, and then some computed information was passed on to physics 2. The problem is that that information contains error, and we want to know what the effect of that transferred error is. And our technique is to define auxiliary quantities of interest and to solve auxiliary problems in order to estimate the error in the transferred information. And if you have an iterative scheme, you not only have transfer of error within an iteration, so from physics 1 to physics 2, but also between iterations. When I think about this as being a single iteration, the error in this solve of the 2 physics certainly is propagated forward to the next solve and so forth. So we need to estimate both within iteration error and between iteration error. So let me give you an example of a simple coupled system of ODEs. And this we call one-way coupling because you see that I can solve the system for U1 without knowing U2, but the solution to U1 appears in the right-hand side of the elliptic equation for U2. And the quantity of interest I'm interested in is the solution to U2 at a particular point. Okay, so if I pick 2 reasonably fine meshes and solve it, then the primary error in the quantity of interest, that is the error that comes from the discretization of the U2 system, is 0.0042. And the transfer error, that is the error in this solution that comes from the fact that the solution to this problem formed the right-hand side for U2 is, well, is a 1/7 of it. So it's not huge, but it's not trivial. If I start off with 2 coarse grids and I just refine the second grid according to the local discretization error in this grid and leave this grid alone, then I get a nonsense solution. Although I've reduced the primary error, the discretization error, in this domain to an acceptable quantity, the transfer error that I get, or that is the error that I've inherited by solving this problem poorly, just dominates the solution. You want to be able to identify that and do something about it. If I start off with 2 coarse meshes and resolve both meshes according to both the transfer error and the local discretization error, then this is the solution I get. I find that I can get away with a very coarse mesh for U2, even though I'm interested in that solution, but I have to refine the U1 mesh a lot more because I am actually using the derivative of this mesh in the right, or this solution rather, for the right-hand side of this piece here. Now, this is not systematic error reduction, which we heard about yesterday, but it is informing the user how well you need to solve each piece in order to get the accuracy that you desire in the quantity of interest that you are concerned with. So this is not systematic error reduction, but it's I would say something along the way. What is the second major problem with operator decomposition? That is the adjoint to the operator decomposed, or the decomposed problem is not equal to the adjoint of the combined system. And this difference is a measure of the impact of operator decomposition on stability. And so there's quite a bit of work. It's non-trivial to get the appropriate adjoint. And additional work is required to obtain a computable estimate. And if you just say, well, I don't care about that, I'm just going to use the adjoint to the coupled system, then you can cause yourself some grief. You can get inaccurate estimates. So as one example, we looked at the flow past a heated cylinder and solved the heat equation in the solid and the Boussinesq system in the fluid. And the quantity of interest is the temperature in the center of the cylinder. There is the fluid mesh resolved around the cylinder. Now, if you perform things naively, then this is the mesh that you are required to use in the solid, with refinement about the edge of the solid, because I am calculating the thermal flux at that edge and transferring it to the fluid. If you perform the analysis correctly and implement an inexpensive correction to account for the transfer error, then you can get away with a much, much coarser mesh in the solid. And this actually also improves the convergence of the solution with mesh size H. One other system we've looked at is multi-rate differential equations, where you have a coupled system of ordinary differential equations that operate on very different time scales. So what you'd like to do is, say, solve the fast system with some explicit scheme and solve the slow system with an implicit scheme and iterate between the two. So here's an example where I have two fast components and a slow component. And under these circumstances, all I want you to get from this is that we are able to accurately estimate both the transfer error, or the error due to the coupling, and the error due to the solution of the individual components with the appropriate, this was a discontinuous Galerkin scheme actually. So where are we currently or hope to take this work? Well, we're trying to look at efficient methods, which we call block adaptivity, because you are going to run into a lot of problem, or let me say this, interpolating between grids, or when you readapt your grid and interpolate from the previous solution, you can introduce very large errors, as well as having to reload balance on a parallel machine. So you want to change your adaptive scheme or change your mesh as infrequently as possible, and so we have an idea of block adaptivity to enable us to do that. We're looking at, obviously, extending to multi-rate partial differential equations and multi-rate partial differential equations coupled to ODEs and SDEs. The target applications that I am working with collaborators in Oxford that may be of interest to this community is to look at cardiac function. We're looking at finite elasticity deformations, and until the previous talk, I perhaps naively hoped that I was going to be able to get away with coupling that to the monodomain and bidomain equations. I think I'll start there, but clearly that's not the end of the story. And also looking at the coupling of fluid flow and finite amplitude elastic deformations to look at arterial flows. So thank you.